Deep in the tropical rainforests of Malaysian Borneo lies one of Southeast Asia's largest infrastructure projects, the Bakun Dam. The Bakun Hydroelectric Dam, located in Sarawak on the Spillway River, is a massive concrete-faced rockfill dam. It's part of Malaysia's ambitious plans to generate hydroelectric power to fuel industrial growth and economic development. Here are some quick facts. Construction began 1996 after years of delay. Completed 2010. Type: hydroelectric dam. Height: 205 meters, making it one of the tallest dams in Asia. Capacity: 2,400 megawatts. Reservoir size: about 695 square kilometers, larger than Singapore. Diversion tunnel is one of the most important temporary structures in dam construction. Its main functions are: 1. Diverting river flow. Before the dam wall is built, the river must be kept out of the construction area. A diversion tunnel channels the river around, or sometimes under, the dam site so that the riverbed is dry and safe for construction. 2. Providing a dry working area. With the river flow diverted, workers can excavate, build the dam foundation, and pour concrete without water interference. This ensures stability and safety during construction. 3. Flood control during construction. The tunnel is designed to carry normal river flow and possible floods during the dam building period. This prevents damage to works under construction and reduces the risk of flooding downstream. 4. Temporary water passage until reservoir filling. Once the dam body reaches a safe height, the diversion tunnel is closed with gates. The river is then allowed to flow through the dam's spillway or outlets until the reservoir begins filling. 5. Emergency use, sometimes. In some projects, the diversion tunnel is modified to become a permanent flood or low-level outlet tunnel after construction. A diversion tunnel's function is to bypass river water safely around the dam site during construction, keeping the foundation area dry and stable until the dam is complete. In simple terms, the 3 diversion tunnels kept the Spillway River out of the dam construction zone so it could be built safely and efficiently. They were sized to handle floods and large flows, which is crucial in tropical river systems. Multiple tunnels meant redundancy and flexibility, useful during both construction and the early impoundment phase. One tunnel was even converted for use during impoundment and downstream release. The Bakun Dam is not just massive, it's a feat of engineering. Let's break down its main structural features. 1. Dam type: concrete-faced rockfill dam, CFRD. The Bakun Dam is a concrete-faced rockfill dam, or CFRD for short. This means it's made mostly of compacted rock, with a concrete slab on the upstream side that acts as a waterproof barrier. Why this design? Because it's ideal for the rocky terrain and heavy rainfall in Sarawak. CFRDs are also more flexible and resistant to seismic activity. Now let's talk numbers. Height: 205 meters, about 672 feet. One of the tallest dams in Southeast Asia. Length: around 750 meters, about 2,460 feet. Volume of rockfill: about 16.7 million cubic meters. Reservoir surface area: roughly 695 square kilometers. That's almost the size of Singapore. Structure of a CFRD. Here's a breakdown of its main components. Rockfill embankment, made up of compacted rock materials, provides the main structural support and resists the water load through mass and friction. Constructed in layers with varying sizes of rock, becoming finer toward the top and the face. B. Concrete face, slab, placed on the upstream face of the rockfill embankment, made of reinforced concrete panels. Acts as the impermeable barrier to prevent water seepage through the dam body. C. Plinth, a reinforced concrete structure at the base of the concrete face. Provides a watertight connection between the concrete face and the dam foundation, bedrock. D. Joints and water stops. Between concrete slabs, Flexible joints and water stops are installed to absorb movement and ensure water tightness under thermal and structural stresses. The concrete face prevents water seepage, withstands environmental forces, accommodates settlement, and enables flexible, economical construction. Power intake. The power intake is a crucial component of a hydroelectric dam. It controls and directs the flow of water from the reservoir into the penstocks, which then deliver the water to the turbines in the powerhouse. Key functions. 1. Control water flow to the turbines. 2. Prevent debris from entering the turbines. 3. Ensure safety by enabling shutdown during emergencies. 4. Minimize head losses for efficient energy conversion. Power intake in Bakun Dam. 1. Location. The power intakes are integrated into the left abutment of the dam. There are 8 power intakes, corresponding to the 8 turbine units in the powerhouse. Each intake is connected to a penstock tunnel that leads to a turbine. 2. Design features. Inlet elevation, designed to draw water from the optimal level in the reservoir, around elevation 205 meter, ensuring efficient flow and minimal sediment intake. Intake structure typically consists of trash racks, gate shaft and gate chamber and transition to penstock. Hydraulic design, shaped to allow smooth water acceleration with minimum turbulence or vortex formation. 3. Trash racks, installed at the front of each intake to filter out debris, logs, branches, fish, etc. Constructed of steel bars, angled for easy cleaning. Prevents clogging and protects turbine machinery. 4. Control gates. Vertical lift or wheel gates are used to control or shut off the water flow. Housed within a gate shaft, operated remotely from the powerhouse control room. Essential during maintenance or emergencies. 5. Transition to penstocks. After the control gate, water enters a transition section that connects to a large steel line pressure tunnel or penstock. The design of this section minimizes pressure loss and prevents cavitation. Hydraulic considerations. Flow rate. Each intake is designed to handle approximate 160 to 180 cubic meters per second. Varies depending on unit operation. Head height. Bakun has a hydraulic head of about 190 meters, giving significant potential energy. Energy loss minimization. Intake geometry, bell mouth, streamlined, reduces losses due to friction and flow separation. Spillway system. To control flooding, the dam has a massive spillway system. This safely releases excess water during heavy rains. Without it, the dam could overflow or fail. 5. Reservoir, Bakun Lake. Behind the dam is Bakun Lake, one of the largest man-made lakes in Asia. It holds billions of cubic meters of water, but it also submerged entire forests and villages. Main functions of a power intake. 1. Direct water to the turbines. The intake channels water from the reservoir into the penstocks, large pipes, that carry it down to the turbines in the powerhouse. It controls how much water is allowed to flow for electricity generation. 2. Control water flow. Equipped with gates or valves, the intake regulates the amount of water entering the turbines depending on electricity demand. It allows operators to start, stop, or adjust turbine operations safely. 3. Protect turbines from damage. The intake is fitted with trash racks, grills/screens, to filter out debris such as logs, branches, and waste that could damage turbines. Sediment and ice are also managed to prevent clogging. 4. Maintain efficiency and safety. Designed to minimize turbulence, cavitation, and air entrainment so water enters the penstock smoothly. Ensures efficient conversion of hydraulic energy into mechanical energy at the turbine. 5. Emergency shutoff capability. In case of emergencies, turbine failure, or maintenance, intake gates can be closed to stop water flow instantly. In summary, the power intake acts as the gateway of water in a hydroelectric dam. It regulates and directs reservoir water safely into the penstocks for electricity generation, while protecting turbines and ensuring efficient operation. Spillway system. To control flooding, the dam has a massive spillway system This safely releases excess water during heavy rains. Without it, the dam could overflow or fail. 5. Reservoir, Bakun Lake. Behind the dam is Bakun Lake, one of the largest man-made lakes in Asia. It holds billions of cubic meters of water, but it also submerged entire forests and villages. Main functions of a spillway. 1. Control excess water, flood management. The primary function of a spillway is to safely release excess water from the reservoir when it rises above the maximum operating level. This prevents overtopping of the dam, which could cause structural failure. 2. Maintain safe reservoir level. By controlling how much water is released, the spillway ensures the reservoir stays within its designed storage capacity, protects the dam, power intake, and surrounding environment. 3. Safe energy dissipation. When water flows over or through the spillway, it carries huge energy. Spillways are designed with energy dissipators, stilling basins, flip buckets, plunge pools, to reduce erosive power before water re-enters the river downstream. 4. Assist in flood routing. During extreme floods, spillways regulate and pass floodwaters downstream in a controlled way, protecting both the dam and communities downstream. 5. Support hydropower operations, indirectly. Although water for electricity is usually drawn through power intakes and turbines, the spillway ensures turbines are not overloaded with excess water. Reservoir storage is optimized for power generation and flood control. 6. Emergency water release. In case of mechanical failure, unexpected floods, or maintenance, the spillway serves as an emergency release valve for the dam. Types of spillways in hydroelectric dams. Overflow, OG, spillway, water flows over the crest, common in concrete gravity dams. Chute and channel spillway directs flow down a steep channel, often with energy dissipators. Shaft, morning glory, spillway, funnel-shaped inlet leading to a vertical shaft. Side channel spillway, flow enters parallel to the dam axis, then turns into a channel. Saddle or bypass spillway, built away from the main dam, often in natural depressions. In summary, a spillway in a hydroelectric dam functions as the safety valve of the reservoir. It automatically or manually releases excess water, prevents overtopping, dissipates dangerous energy, and protects both the dam structure and downstream communities, while ensuring stable conditions for continuous hydropower generation. How dams boost the Malaysian economy. The Bakun case. While the Bakun Dam has its share of controversies, it's also brought major economic benefits to Malaysia, particularly in terms of energy, development, and regional growth. Let's take a closer look. 1. Cheap renewable energy. Hydroelectric dams like Bakun generate clean, renewable energy from flowing water, with low operating costs once the dam is built. Bakun's capacity, 2,400 megawatts. It helps reduce reliance on coal and gas, saving billions in fuel imports. Lowers Malaysia's carbon emissions in the long run. By generating large amounts of electricity locally, Malaysia improves energy security and reduces its exposure to global energy price fluctuations. 2. Powering industrial growth. The Bakun Dam was built to power heavy industries, especially in the Sarawak corridor of renewable energy, SCORE. This includes aluminum smelters, steel manufacturing, petrochemical plants. These industries attract foreign direct investment, FDI, create high-paying jobs, and help Malaysia move up the value chain. 3. Boost to regional development, especially in East Malaysia. Large infrastructure like Bakun brings roads, bridges, and connectivity to rural Sarawak, one of Malaysia's most remote and underdeveloped areas. Improved transport networks, better access to education and healthcare, job creation for local communities during and after construction. This helps reduce the economic gap between Peninsular Malaysia and East Malaysia. 4. Revenue generation. The dam generates income through electricity sales to utilities and industries, potential export of power to neighboring countries, like Indonesia and Brunei, long-term returns on investment from public-private partnerships. By exporting surplus electricity, Malaysia can turn hydropower into a regional economic advantage. Powerhouse. The Bakun Dam Powerhouse is the heart of the hydroelectric project where the potential energy of stored water is converted into electricity. The powerhouse is located underground, on the right bank of the Spillway River, near the base of the Bakun Dam in Sarawak. At the base of the dam lies the powerhouse, housing 8 turbines. Each turbine generates 300 megawatts, giving the dam a total capacity of 2,400 megawatts. Building it underground provides stability, strong gray waka rock foundation, and safety while minimizing environmental and surface land use. 1. Turbines and generators. Equipped with 8 Francis-type turbines, each rated at 300 megawatts. Total installed capacity, 2,400 megawatts, making it one of the largest hydropower stations in Southeast Asia. 2. Underground cavern. The main powerhouse cavern is about 52-meter wide, 222-meter long, and 66 m high. Adjacent transformer cavern and busbar galleries house supporting electrical equipment. 3. Water flow. Water from the reservoir enters through the power intakes, passes via penstocks, large tunnels, drives the turbines, discharged back into the river through tailrace tunnels. 4. Transmission. Generated power is stepped up by transformers and transmitted via high-voltage transmission lines. Bakun originally transmitted electricity through a 275 kV and 500 kV network to serve Sarawak's demand and later to supply the Sarawak corridor of renewable energy. Score. Functions of the powerhouse. Electricity generation. Converts water energy into usable electrical power. Grid stability. Provides baseload power for Sarawak's industries and communities. Support for SCORE. Supplies renewable energy to energy-intensive industries like aluminum smelting, ferroalloy, and silicon plants. The Bakun Powerhouse is a massive underground facility with 8 turbines generating 2,400 megawatts of renewable electricity, forming the backbone of Sarawak's hydropower system. Main functions of a powerhouse. 1. Houses the turbines. Water delivered through the penstock strikes the turbine blades. The turbines convert the kinetic and potential energy of water into mechanical, rotational energy. 2. Houses the generators. The turbines are directly coupled to generators. As the turbines spin, the generators convert mechanical energy into electrical energy. 3. Controls and distributes power. Inside the powerhouse, electrical equipment, transformers, switchgear, control panels, regulate voltage and frequency. Power is then transmitted to the grid for public and industrial use. 4. Provides safe operation and maintenance. The powerhouse layout includes access for operators, monitoring systems, and safety mechanisms. Allows inspection and servicing of turbines, generators, gates, and valves. 5. Discharges water back to the river. After passing through turbines, water flows into the tailrace channel and rejoins the river. Ensures continuous ecological flow downstream. The powerhouse in a dam hydroelectric project functions as the energy conversion center. It houses turbines and generators that transform the water's hydraulic energy into usable electric power and then safely transmits it to the grid. A Rockfill dam is one of the most common types of embankment dams, built mainly with compacted rock fragments and usually featuring an impermeable core or facing to stop seepage. It is especially suitable for regions with abundant rock material near the dam site. A Rockfill dam is a type of embankment dam made primarily from compacted rock fragments. Its main functions include 1. Water storage. Like other dams, Rockfill dams are built to store water for irrigation, drinking, industrial use, and hydroelectric power generation. 2. Flood control. They help regulate river flow and reduce the risk of downstream flooding by controlling water discharge. 3. Hydroelectric power generation. Rockfill dams often support hydroelectric power plants by creating a reservoir with sufficient waterhead for turbines. 4. Irrigation support. They provide a stable water supply for agricultural irrigation during dry periods. 5. Water supply regulation. They help manage seasonal water availability, ensuring consistent supply even during droughts. Key features of Rockfill dams. The dam body is made of compacted rock fragments. Usually has an impervious core or face, like clay or concrete, to prevent seepage. Good for sites where rock materials are abundant and foundation conditions are suitable. In summary, the function of a Rockfill dam is to retain and control water for various uses such as water supply, flood control, and power generation, while using rock materials as the main structural component. Structure of a Rockfill dam. 1. Main body shell. Constructed from blasted or quarried rock, compacted in layers. Provides the strength and stability of the dam. 2. Impermeable zone, core or facing. Prevents water from seeping through the dam. 3. Filter and transition zones. Sand or gravel layers placed between the rock shell and core. Prevent migration of fine soil particles and control seepage. 4. Drainage zones. Zones of free-draining rock that safely collect and discharge seepage water. Protect the core and reduce water pressure inside the dam. 5. Upstream protection. Riprap or large stones on the upstream slope to resist wave action. Advantages of Rockfill dams. Flexibility, good performance on weak foundations and in seismic zones. Use of local materials, rock, gravel. Faster construction compared to large concrete dams. Can be built to great heights, for example. Nurek Dam in Tajikistan, 300 meter, one of the tallest dams in the world. In summary, a Rockfill dam is an embankment dam built mainly of compacted rock with an impermeable core or facing. Its function is to store water safely for hydropower, irrigation, and flood control, while offering stability, earthquake resistance, and cost efficiency, especially in areas with abundant rock resources. The power tunnel in dam construction serves a crucial role in hydroelectric power generation. Its main function is to convey water from the dam's reservoir to the powerhouse where turbines are located. Specifically, the functions of a power tunnel are: 1. Water conduction. It safely and efficiently transports water from the reservoir or intake structure to the turbines in the powerhouse. 2. Pressure maintenance. The tunnel maintains the water pressure needed for effective turbine operation, enabling the conversion of potential energy from stored water into mechanical energy. 3. Flow regulation. It controls the flow rate of water entering the turbines, which affects power output. 4. Protecting flow. It prevents water loss and minimizes turbulence or energy dissipation between the reservoir and turbines. 5. Structural support. It provides a durable passage that can withstand high water pressures and geological stresses. In short, the power tunnel acts as a pressurized conduit that delivers water to the turbines, enabling the generation of electricity in a hydroelectric dam system. The Bakun Dam was actually first proposed in the 1980s, but due to environmental concerns, financial constraints, and the Asian financial crisis in 1997, the project was delayed multiple times. Finally, after years of political debate and changing contractors, the project was completed in 2010. Dams in Sarawak offer economic potential and a step toward a greener energy future, but they come with heavy environmental and social costs. The challenge is to balance development with human rights, biodiversity, and cultural survival. Should Sarawak continue building more dams, or focus on energy efficiency, rural electrification, and solar alternatives? Dams can light up cities and grow economies, but they must also uplift the people closest to the rivers. If the government truly wants to build a better Malaysia, it must start by making life better for those who have sacrificed the most. They once lived by the rhythm of the river, planting when it rose, fishing when it calmed, celebrating when it flowed free. The river wasn't just water. It was memory, identity, and home. But when the dam came, everything changed. Villages were swallowed, fields disappeared, and with them a way of life. Promises of progress arrived in concrete walls and silent waters, but the voices of those who lost everything still echo, not in headlines, but in the empty spaces where homes once stood. So while the Bakun Dam has come with costs, especially environmental and social, it has also unlocked powerful benefits for Malaysia's economy: clean energy, industrial development, jobs and investment, regional growth, energy security. The key now is to make sure these benefits are shared fairly, and future projects are done with better transparency, sustainability, and care for local communities.